Hi everyone. We are group 4, and we're going to be presenting on effects of chemical properties on wine quality. My name is Peggy Huang.
I'm Cody Capitalist.
I'm Sharon Clalley.
I'm Alan Lin.
And I'm Zahalini.
So first, we're going to briefly go over the background of our study. So this sample was obtained from Portugal. It has a sample size of 4,898 and is useful for wine evaluation, certification, quality assurance, and improving production process. And the wine quality is measured on a scale from 0 to 10, 0 being very bad to 10 being excellent. This dataset was obtained from UCI Machine Learning Repository, Center for Machine Learning and Intelligent Systems. It is a confirmatory observatory study of conclusions made by Cortez et al. 2009.
These are the X and Y variables from the dataset, with the exception of X12. We created this new variable when merging the red and white wine datasets to be able to differentiate the two. Using a data mining model, Cortez et al. Showed that wine preferences have a strong relationship with various physiochemical properties. Our aim is to confirm that this study through the use of linear modeling and analysis. Studies such as this may be used to confirm research on human taste, which is, according to the paper, the least understood sense. Additionally, it may be used to form a statistically backed method for a more technical winemaking approach. Quantitative measurements are, as opposed to qualitative ones, may allow winemakers to more accurately assess the quality and how to improve it.
So our first research question is to examine whether pH, sulfate, and alcohol concentration have a significant impact on wine quality. The hypothesis is that the physicochemical properties, such as pH, sulfates, and alcohol concentration, have a significant impact on wine quality. The variables were fitted to a linear model using the following equation. Quality equals to pH, sulfate, and alcohol. pH being X9, sulfate is X10, alcohol is X11. So the reduced model is shown here with degrees of freedom n minus p. The full model also has degrees of freedom of n minus p. According to the R output, the F statistics is greater than the F critical value, and a statistically significant p-value less than our alpha values, less than 0.05. This leads us to reject the null hypothesis and conclude that pH, sulfates, and alcohol concentration does have an impact on wine quality. So we did the diagnostic process on model building. For the residual plot, we can see that the plot showed constant variance and normal errors as residuals seem to distribute evenly above and below the zero line. The Brown-Forsyth test will help us determine whether the residuals have constant variance. And we also did a Shapiro test to test for the normality. The Shapiro test challenges the following hypothesis. The null hypothesis states that data follows a normal distribution. The alternative hypothesis says that data violates from normal distribution. The normal QQ plot and histogram as shown below seem to follow normal distribution. However, based on the Shapiro-Wilk normality test, the p-value is less than the alpha value we set, which is less than 0.05 significance level. We will reject the null hypothesis and conclude that data violates normal distribution. The data points tend to follow the curve without outliers. So next, we did the Brown-Forsyth test. So this test challenges the following hypothesis. The null hypothesis states that the residuals have constant variances. The alternative hypothesis says that the residuals do not have constant variances. According to the output below, there is a violation on constant variance. And for the multicollinearity, we also did the VIF test. So based on the plot above and the VIF values, there is not much multicollinearity issue. So for the WLS model, we can see that the X9 variable, which is the pH, is still insignificant after performing the WLS model. This is consistent with the literature. And for the bootstrapping, from the confidence interval shown on the right, all of them do not cross zero. So the first one shows the X9 variable pH, and then second one shows the sulfate, third one shows the alcohol concentration. So sulfate's pH and alcohol concentration does not have a significant linear impact on wine quality. And for the k-fold cross-validation, based on the results shown above, The model number 6 is better given the lower RMSE value.
This research question examines whether pH X9 has a significant impact on the quality of white wine given fixed acidity X1 and volatile acidity X2. The hypothesis is that pH will have a significant impact on the quality of white wine given fixed and volatile acidity are considered. The null hypothesis is that B9 is equal to 0, and the alternative hypothesis is that it isn't equal to 0, with the following reduced and full models. The summary ANOVA table showed that the multiple R-squared value was 0.05 with a p-value less than 0.05. This might indicate that the pH does have a significant impact on the quality of white wine given fixed acidity and volatile acidity. The residual plots were created against each variable. The residuals roughly fall within the horizontal band centered around 0, although the horizontal points may indicate that there is a systemic pattern in the errors of the regression model. The Shapiro-Wilk normality test was performed, which identified a p-value less than 0.05. We can conclude that the data isn't normally distributed. This is further demonstrated in the QQ plot, where the points create a wave pattern along the line. The Brown-Forst test was performed based on 3 groups. Given that this value is less than 0.05, we can conclude that the data is not constant. The VIF test was performed, which resulted in values all less than 10. We can conclude that there isn't an issue with multicollinearity. Additionally, the following graphs look for outliers and influential points. It can be concluded that there are outliers present on the x-axis, but there aren't any influential points given that the Cook's distance values are all less than the 20th percentile. In addition to running OLS regression, WLS and robust regressions were performed, with WLS demonstrating a slightly higher increased value and robust showing a slightly decrease in values compared to the OLS model. The confidence interval from the bootstrapping for the WLS are shown on the left, and the confidence intervals for the bootstrapping for the robust models are shown on the right. Given that B9 contains a 0 for both WLS and robust, we can conclude that the null hypothesis cannot be rejected and there isn't a significant linear impact.
Question 3 explores whether or not the density of the wine X8 has a significant impact on the quality of the white wine, given the free sulfur dioxide levels X6 and the total sulfur dioxide levels X7. Here we can see that the reduced model and the full model, with the null hypothesis being whether beta 8 is equal to 0 and the alternative hypothesis being if beta 8 is not equal to 0. We can see the reduced model and the full model here, with the degrees of freedom for both models being n minus p. Moving on to the model summary ANOVA table, we can see the corresponding R-squared value as well as the p-value, in which we have significant evidence to suggest that wine density does indeed have a significant impact on the quality of the white wines. However, before we can make any conclusions, we need to first check the assumptions of multilinear regression first. We take a look at the residual plots of the predictor variables as well as a QQ plot and Shapiro-Wilk test to test for linearity and normality issues. The residuals fall within the horizontal line at 0 for all 3 residual plots, suggesting that linearity is upheld. However, with a p-value of less than 2.2 to negative 16 power in our QQ plot over here, it suggests that the residuals are distributed unevenly, thus normality is violated. Moving on to the constant variance and multicollinearity with our Brown-Forsyth test and our variance inflation factors. From the BF test, we can conclude with a p-value of 2.305 to negative 10th power. We can conclude variance on error terms is not constant, thus constant variance is violated due to it being less than the alpha value of 0.05. As for multicollinearity, we can look at the VIF values for all 3 of the predictor values, in which they are all less than 10. So we can see that there's no multicollinearity issues there. Moving on to the outliers and influential points, we can see on our hat matrix that there are clear X outliers, and from our DF beta plots, there are influential points for all 3 of our predictor variables, showing the presence of influential cases on our regression coefficients. From our Cook's distance plot, we can see that there are points with relatively higher Cook's distances. However, they do not hold influence on our fitted points, as they do not exceed the boundaries of the 20th percentile. Due to the violations we had earlier, we need to apply remedials via WLS regression and robust regression methods. For the unequal error variance, we applied WLS regression, and for the other outliers, we applied robust regression methods. We can see the model summaries of these remedial methods as well as the new models given here and here. After bootstrapping, we also obtained new confidence intervals, and since 0 do not fall within any of these confidence intervals, we can reject null hypothesis and conclude that density does in fact have a significant impact on the quality of white wines given free sulfate levels and total sulfate levels.
And in research question 4, we are examining that if X1 has a significant impact on the white wine quality compared to X2. So based on the model we have, we can conclude that the X1 has a significant impact on the wine quality compared to X2. And we have a null hypothesis which sets the beta 1 interact 2 equals to 0 to see if we can set the hypothesis. So for the model building, we did the ground force test, which get a p-value which is larger than alpha equals 0.05. And we can say that variance of the error terms is constant. And for the normality, we use the Shapiro test and get a p-value is smaller than alpha. So the residuals in the dataset are not normally distributed. And the residual plots are also obtained to see the constant variance and the linear trend. And we found that it is statistically significant. Based on that, we also did the WLS and OLS models. We can see that there are differences between the OLS values and the WLS values. To adjust the measures, we also use the rubbers and use the bootstrapping. After the bootstrapping, we can see that the beta 1 interact 2 does not equal to 0. And for this, we need to reject the null hypothesis and conclude that X1 has a significant impact on the wine quality compared to X2.
For research question 5, we examined if density and sulfate content have the same linear effect on wine quality for white versus red wines, with the type of wine being a categorical variable and the interaction effects modeled accordingly. The conclusion that we can make from this linear model, the OLS-based linear model, is that a separate test on the significance of the interaction terms, those being density, type 1, and type 1 sulfates, we conclude that the linear relationship between sulfate content and quality is affected by the type of wine, but the relationship between density and quality is not affected in the same way. Next, we'll look at diagnosis of the model and any remedial procedures that we have to perform. So the residual plots of the model, of the model's two continuous variables are shown on the left. They have approximately equal grouping around 0 in both cases, as well as a seemingly constant variance. Sulfates, which is on the right side, or excuse me, the right of the two models on the left, seems to show a slight linear trend downwards as the graph gets more and more to the right, but this is likely explained by the interaction with wine type, which was found to be statistically significant in the OLS model. Sorry, go back.
Oh, my bad.
Next, the QQ plot on the right side indicates that while the data does follow a general trend of the 45-degree line upward, there's still a significant non-normality in the data. Next, the graph on the left is a plot of hat leverage on the x-axis and studentized deleted residuals on the y-axis, with each data point scaled by its Cook distance.
Oh.
From what we can see is that there's one extreme outlier in both x and y, that being on the top right, and on the bottom right there are 3 major outliers in x. A Brown-Forsyth test was then used to evaluate the unequal variances between the two categorical groups, white and red wines. The difference was found to be statistically significant, and so these two groups have unequal variances. To evaluate the unequal variances in the remaining continuous variables, a Bruch-Pagan test was used, but did not find a statistically significant difference, which indicates no heteroscedasticity in density and sulfates. Next, using the variance inflation factor, which was modified according to degrees of freedom due to the presence of the interacting categorical variable, there is very little evidence of multicollinearity in the model due to the values of well below 10. In looking for influential points, 3 DF betas plots shown on the left, and it's quite obvious that many of these points exist above, or rather outside the limit bars for density and sulfates. And note that on the bottom left, the categorical variables, it's clear that influential points typically exist for red wines, but not really for white wines. And lastly, on the right, we have the Cook's distance plot. We can see a few separate data points have significantly higher Cook's distances than the rest. However, none of these are above the 20th percentile, which corresponds to a Cook's distance of greater than 0.33. So we can conclude that none of these have a minor influence even on any of the, or excuse me, on all fitted values. Now for remedial measures. We found that outliers existed in the model and that the model violated normality. To remedy this, we used a robust regression and then bootstrapped that robust model for the final model used. So as you can see on the bottom right, the confidence intervals developed by the bootstrapped model indicates the same conclusions actually that were made in the OLS model, and that is that the interaction only exists between the wine type and sulfate content, not between density and sulfate content.
So here's the summary of our k-fold cross-validation. As you can see from our previous research questions, we all had an RSME model on our questions. And across the board, our RSME values were pretty low, indicating a relatively good fit on the data. These values change very little when adding variables, suggesting that using too many predictor variables may cause overfitting.
So this study, as mentioned before, being a confirmatory observational study, it confirms the result of the previous work by Cortez et al. In showing that perceived wine quality does have a linear relationship with the physiochemical characteristics of the wine. So in the models, while not all combinations of predictors were tested, there is significant evidence that certain properties do have a strong linear relationship with the quality rating. Additionally, as I mentioned before, there is evidence of interaction effects with the type of wine being red or white. These were found for at least one variable, but it suggests that different chemical properties could be more or less important to people's tastes, depending on the type of wine, and warrants further investigation. And lastly, because the dataset utilizes a numeric response variable that is actually an integer with a somewhat low range, this model may be more suited, or this data may be more suited to an ordinal logistic regression model in order to compare probabilities of higher ratings. But that is beyond the scope of this class. And regardless, the group can still develop insightful conclusions from the linear model that we just described.
And to conclude, all the models and tests we have all show a very high predictive power and strong linear relationships between our variables. Also, the analysis of our predictors show that the variables have both impacts on the white and red wines. We also have some references in the slides, and we studied in the next slide here to show our citation and the information that we have used.
All right, thank you for listening to our presentation.